This is Jan2007 A21 Module 4. A mass executes simple harmonic motion along horizontal direction. The displacement x of the mass is measured from the centre position 0, where the displacement to the right of O is positive and the displacement to the left of O is negative. The amplitude of the motion is x0. Figure 4.1 shows the situation. At particular points in the motion of the mass, Table 4.1 indicates the force with its direction, the displacement and the velocity as the mass executes simple harmonic motion. Complete the blank table in Figure 4.1. Now, we know the object has got a maximum velocity as it moves through its centre position always, and therefore the displacement of the object is 0 at that point. The force at that point, if it's got a maximum velocity, it's got no acceleration. I'll just write that in, no accel, and therefore the resultant force is also 0 because of that. However, if the force is maximum and it's going to the right, so the force is maximum and it's pointing to the right, if I just put that onto the graph, the force and acceleration are always in the same direction. They're always directed towards a fixed point at the centre. So if they're pointed to the right, the force can't be in this direction because it isn't pointing towards the centre, and therefore there's the direction of the force. And that means that your displacement of the particle is negative. So if it's maximum acceleration occurs at the edges, and therefore it's minus x0. And the velocity at that point where it's changing direction is 0. There's half a mark each for those, and they round down unfortunately, which is a bit annoying. Figure 4.2 shows the velocity of the mass, how it varies with time. On the axes provided, draw a graph to show how the displacement varies with t. Now this graph, the velocity graph there, is a minus sign graph. You know that whenever you take the gradient of a displacement time graph, you get velocity. So here the velocity is equal to 0, and therefore you've got a flat part of the graph here. So this is some kind of cosine graph, but as yet you're maybe not sure whether it's positive or negative. But you can tell then by looking at the next part of the graph, you can tell that whenever the velocity is minus and maximum, that means that the graph is going down through, it's coming up, going down, yes, it's going down through here to get a negative and maximum gradient. And so your graph is going like that. And then that just gets you the rest of your graph, of course. But it's hard, I've taught you to do this all the way around. It's really thinking backwards. So if I just check that I'm right here, and if I was wrong, I would rub it out and start again, if I'd done it in pencil, of course. Here, my gradient of my displacement time graph is 0, and that corresponds. Here, the gradient is negative and maximum, so that corresponds. Here, it's 0 again, and that corresponds. And just to check, last one, positive and maximum again up here, so that's fine. The amplitude of the motion is 50 millimetres and the maximum velocity is 0.35 metres seconds to minus 1. Calculate the frequency of the motion. And therefore Vmax equals x0 omega, and omega is equal to 2 pi f, so we need to use that equation by 2 pi f. And so f is going to be Vmax over x0 times 2 pi. And so that's 0.35. Everything has to be in metres, seconds to minus 1. That's 0.05 metres times 2 pi. And that gives you an answer of 1.11 hertz. Damping often occurs in oscillating systems. Explain the meaning of the term damping. So damping is a force, a resistive force, which causes the amplitude of an oscillation to decrease. A system consists of a spring suspended from one end of a mass suspended from one end of a helical vertical spring. The system has light damping. The mass is displaced to a point P and released. Commencing at P on figure 4.3, draw a graph to show how the displacement of the mass varies with time. And therefore what we're going to show is lightly damped oscillations, so steadily decreasing amplitude. And because the scale is small, I'm just going to mark off each centimetre. And therefore it's going to go a wee bit smaller, a little bit smaller again, smaller, something like that. And then the system is now subjected to heavy damping. The mass is displaced to a point Q and released. Commencing at Q, draw a graph to show how displacement varies with time. And so if I just show, so what's going to happen is going to come to rest without really any oscillation at all. And it's just going to do something like that there. Suggest how the heavy damping in B part 3 might be achieved. So I'm suggesting attach a piece of card with a large surface area or perpendicular to direction of oscillation, or very often they suggest place mass in water or oil.